Hello everyone, this is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Aula Institute of Technology. Today I'm going to talk about a topic of electrical circuit and network, the lesson plan of the subject. Now, today's topic of discussion is Maximum Power Transfer Theorem and the problem of Maximum Power Transfer Theorem. Today I'm going to show you that how to solve any circuit using Maximum Power Transfer Theorem. I already make a lecture on this maximum power transfer theorem. That was basically the statement and about the steps to follow to solve any circuit using maximum power transfer theorem. But today, let me discuss on if any problem is given, then how to solve that problem using this maximum power transfer theorem. Look, in a linear active bilateral DC network, the maximum power will be transferred from source to the load when the external load resistance equals to the internal resistance of the source. So this is called maximum power transfer theorem. Now try to understand the meaning of this. Try to develop your knowledge about all the term, all the word which is related with this statement. So for that, you have to consider some topic first. You have to realize some meaning here in a linear. That means circuit should be linear circuit. Then active circuit, bilateral circuit. So the circuit should be linear, active, and bilateral. Do you know what is the meaning of bilateral? Bilateral means if current can flow from the both side of the circuit, that type of circuit is called the bilateral circuit. Like if resistance is connected with the circuit or inductor capacitor is connected with the circuit, then if you connect a voltage or current source, so if this type of element is in a circuit, so no problem from where the current is flowing. So from any side the current can flow. So this type of activity or this property is called the bilateral. Then active means circuit should be energized. That means there should be some voltage source and current source. And linear means it will follow some particular rules. So here we are considering DC network. So these are the three terms are important. The maximum power. Okay, so for this case, the maximum power will be transferred from source to the load. From where to where? From source to the load. When the external load resistance equals to the internal load resistance. We have to remember this, the external load resistance is equal to the external load resistance should be equal to the internal resistance of the source. So we have to calculate the internal resistance of the circuit. Then if the value of the internal resistance of the circuit and the value of the load resistance, that is the external resistance considering here, if these two value is same, then we can say that the power, the maximum power will flow through the circuit. So this is the meaning of maximum power transfer theorem. Now if we consider the below figure, here in this figure, in the given figure, there are some element. Number one is a voltage source is connected, then a 6 ohm resistance, another 2 ohm resistance, and the load resistance is R here for this case, and also a current source connected with the circuit, that is 8 ampere. So one voltage source, one current source, and 3 resistance connected in the circuit. So here consider the below circuit for which we are going to determine the value of load resistance RL. So here our aim is to find this load resistance RL for which maximum power will transfer from the load to source. Sorry, from the source to load. So we have to find these RL. Now the question is, look here, when maximum power will transfer from source to load. That means we already learned it in the previous slide that when maximum power flow, when the internal resistance is equals to, if we consider the internal resistance is RIN, when RINT equals to RL, so this is the condition of flow of maximum power. That means in this question, in this problem, it is written that determine the value of the load resistance RL. So how can we find this RL? And the condition is also given, maximum power will transfer from source to load. So if we can calculate the value of RINT, is the internal resistance, that will be the value of RL, because we know that the property of the maximum power transfer theorem is the internal resistance should be equal to external resistance. So we have to find the external or load resistance. How can we find it? We can find it by calculating the internal resistance RINT from the circuit. So it is important to learn that how to find the internal resistance of the circuit. Then you can easily find out the value of load resistance of the circuit. Now the given circuit can be further simplified by converting the current source into equivalent voltage source as given. So in the previous circuit, in the last slide, in this position a current source was there. So here we convert current source to voltage source. So in the previous slide, there was a current source, and with the current source a 2 ohm resistor was connected parallelly, because we know that if with a current source always the resistance connected parallelly, this way the resistance always connected. So obviously in this position we have to connect the resistance, that will be parallelly connected. But if we convert it from current to voltage source, then what will happen? The value of voltage will set here, and with this the resistance will be connected in series. That is the property of connection between voltage and resistance, and current and resistance. Current source with parallel resistance, voltage source with series resistance. So we simply just convert the value, convert it from current source to voltage source for the simplification of the circuit analysis. I think it is clear to all of you now. So now we have two voltage sources. One is 12 volt, one is 16 volt. Here the RL is present. we need to find the Thevenin equivalent voltage, VTH, and Thevenin equivalent resistance. That means before solving the maximum power transfer theorem, first you have to clear the concept about Thevenin's theorem. I think from my last lectures, you already know that what is Thevenin's theorem, how to solve any circuit using Thevenin's theorem. If you don't know, if you don't have the idea to solve the circuit using Thevenin's theorem, please go through that lectures. I already made 2 lectures on Thevenin's theorem, where in the first lecture I explained the theorem, the steps to solve the circuit, the generalized steps to solve the circuit about Thevenin's theorem, and the second slide of Thevenin's theorem there was a problem, and I show you that how to solve the problem using Thevenin's theorem. So Thevenin's theorem is the most important part to solve the circuit using maximum power transfer theorem. So more than 50% of the problem we can solve using the concept of Thevenin's theorem for maximum power transfer theorem. So first we need to find the Thevenin's theorem, Thevenin equivalent voltage. So 2 things we have to find out. First one is VTH, that is Thevenin voltage. Second one is RTH, and Thevenin equivalent resistance RTH across the load terminals. In order to get the condition for maximum power transfer, by disconnecting the load resistance, the open circuit voltage across the load terminals can be calculated as look. Here we remove the load resistance. So between A and B terminal, there was a load resistance connected with the circuit. So the first step, we just remove the load resistance from here, from this position. In the previous slide, a load resistance was connected between this terminal, A, B terminal. Okay. So we just remove that part from the circuit and then redraw the circuit like this one. So what was first step? Convert current source to voltage source, then remove the load resistance from the circuit. Now, by applying KCL or Kirchhoff's voltage law, we get from the last slide from here that 12 minus 6i minus 2i minus 16 equals to 0. So it's a very simple Kirchhoff's law. So it is 12, look, 12 minus 6i minus 6i minus 2i minus 6i minus 2i then minus 16 equals to 0. So here in the given circuit we just use the simple Kirchhoff's voltage law, and then we find that the current which is flowing through the circuit, that is I equals to minus 0.5 ampere. The open circuit voltage across the terminal AB. So what will be the voltage for this case, open circuit voltage, that is 16 minus 2 into 0.5. So the open circuit voltage is 16 minus this 16 minus 2 into 0.5. Why 2 into 0.5? Because the current here is minus, the current which is flowing through the circuit is minus 0.5. So here the voltage is minus 16 and the current is flowing actually from the opposite direction, from 12 volt to the current coming, the I current is coming from 12, so that is minus 6, so minus 2 into 0.5, because the resistance here is 2, so 2 into 0.5, so the value is 16 minus 2 into 0.5. So VAB, the voltage across the open terminal from where we remove the load resistance from this part, the voltage AB is equals to 15 volt. After that, look the circuit. Thevenin equivalent resistance across the terminal A and B is obtained by shorting the voltage source as shown in the figure. So in the previous figure, there was a 2 voltage source. One source was connected in this location. One voltage source, another voltage was connected in this location. So what is, remember the Thevenin voltage, yes, the Thevenin's theorem. So for finding the internal resistance Req or RTH, we remove the voltage source. If voltage source is there, just simply remove the voltage source. And after removing the voltage source, we have to short the line. So here we short this point. Short means we connect this point with a wire, a conductor. So after that, what is the remaining part of the circuit? Only these two resistance is remaining. That is, one is 6 ohms and another one is 2 ohms. So how these two is connected in this circuit? These two is basically connected series or parallel? Parallelly connected. How? Because the starting and end point same for these two terminals. This is from this node 6 ohms connected. From this node 2 ohms is starting, and here the end point of both the resistance. So you can say that 6 ohms and 2 ohms are connected parallelly. So when it is parallelly connected, then you can say that the value of R equivalent is very simple. 6 into 2 divided by 6 plus 2. So 12 divided by 8. That means it is 1.5 ohms. So in this way, we can find the internal resistance of the circuit. So the maximum power will transfer to the load when, now tell me what is the property of maximum power transfer theorem? Maximum power will transfer through the circuit when load resistance equals to the internal resistance. So what is the internal resistance in the circuit? RTH, which we measure just now, 0.15, that is the internal resistance. So if the value which was connected in this point, that was the load resistance. So if load resistance is equal to the internal resistance, then only maximum power will transfer. That means the value of RL will be equals to Req for the flow of maximum power. So we can easily say now that maximum power will flow or will transfer to the load when RL equals to 1.5 ohms. So it is nothing but we are applying the Thevenin's theorem in this circuit. Now let me talk about the maximum power transfer theorem in AC circuits. The last one was DC circuit and this one is AC circuit. So for AC circuit, consider the below AC circuit. So we consider here a AC circuit, AC network, to which we are going to determine the condition of maximum power transfer and the value of maximum power. So first try to identify what are the parameters, what are the values, what are the elements given in this circuit. AC voltage source, sinusoidal voltage source, the value is 40 angle 0 degree volt. Then what is this? Inductor 4J. This is the value of the resistance. This is capacitance minus 2J, and this is the load resistance. So these are the elements here in this circuit. Now we have to apply maximum power transfer theorem through the circuit. So how can we solve it? So the first step is remove the load resistance from the circuit. That means we have to remove the load resistance from the circuit, and also we need to remove the voltage source from the circuit also. So that is the process to find the impedance. For AC, for DC it was resistance, it is for AC this will be impedance Z. So look, for this circuit, for finding out the maximum power transfer, first we have to determine Thevenin voltage and equivalent resistance. By disconnecting the load impedance, this was the load impedance in this, where the load impedance was connected. In this section, the load Z was connected, ZL was connected. So we just remove it, disconnected the load impedance and making the voltage source short circuit. So making here the voltage source was connected. So we just remove the voltage source, and if it is a voltage source, just short the line. That's enough. The network becomes as shown below. So what will be the network? ZAB. Then ZAB. So the value of ZAB, that means the equivalent impedance of the circuit will be what? Very easy. These two points. That means the 4J, and this will be actually no load resistance, no voltage source. So 4J and 4, these two connected parallelly. So for parallel connection, you know the method, 4 into 4J divided by 4 plus 4J. This is the equivalent impedance across 4J and 4 resistance. Now minus 2J is connected in series with this equivalent resistance. So here simply we need to write plus of minus 2J. That is written here. So put carefully. So after simplified, we'll get the value of Z equals to 2 ohms. Therefore, the condition for maximum power transfer is ZL equals to ZT, that is 2 ohms. So when maximum power will flow through the circuit, we know that when the internal impedance is equals to the load impedance. So you already find the internal impedance. So if that should be equals to Z to H, load impedance, then maximum power will flow. So it's like back calculation type. So the condition for maximum power transfer is ZL equals to ZT, that is equals to 2. Now try to find out the voltage, open circuit voltage, or you can say VTH. The Thevenin voltage of the circuit can be determined by applying the voltage divider rule to the below circuit. I already made a video lecture on this voltage dividing rule. Please go through that one first, then only you can understand. So here VTH is equals to 40 angle 0 degree, that means 40 divided by 4 into 1 plus j, 4 plus 4j, that means 4 into 4 plus j into 4. So that is voltage dividing rules. So if we calculate 40 is the voltage given here, 40 divided by 4 plus j4, into 4, because we are going to find the voltage across VAB, and the parallel resistance across the open terminal is 4. So here the voltage across the parallel resistance is 40 divided by 4 plus J4 into 4. If you calculate, then the value will come 28, simple calculation, 28.29 angle minus 45 degree. So here we convert it from Cartesian to polar form, x plus jy to polar form. So I also make a lecture on this topic. Please first go through that, then it will be easier for you to understand the calculation. Do you know the calculation, how to convert from Cartesian to from x plus jy to r theta? This is r theta polar form. It's very simple, because you know that if it is x plus jy, then x equals to r cos theta and y equals to r sin theta. So if this is the point and the distance from center, suppose this point is P, this is x and y. If this part is x and this part is y, it is r and it is phi. Then what will be the value of r? We know that r equals to r square equals to x square, because this is x, this is y. R equals to root over Pythagoras, x square plus y square. So here the value x and y both are given, so you can easily find the value of r. So r theta now, or r phi. So what is phi here? Tan inverse y by x. So simply using these two formula, you can convert it from x plus jy to r theta form. So for this particular technique, please visit that lecture. That will be better for all to understand the method. So now the RTH is measured, the ZTH, the impedance, load impedance and voltage both are measured for the circuit. So in this way we can solve the circuit of any AC circuit of using the maximum power transfer theorem. So basically maximum power transfer theorem is the modified version of Thevenin's theorem. Now the application of this maximum power transfer theorem. So in electronic circuits, especially in communication system, and signal present at the receiving antenna is of low strength. In order to receive the maximum signal from the antenna, impedance of TV receiver and antenna should be matched. Then only maximum power will flow. The TV receiver impedance and the antenna impedance should be equal. So this is one of the application. Now application in between the audio amplifier and audio speaker. In an audio amplifier with audio speaker arrangement in public addressing system, speaker resistance must be equal to amplifier resistance. in order to transfer maximum power from the amplifier to the speaker. So this is another important application of this maximum power transfer theorem. The next one is in case of car engine starting system. Starter motor resistance must be matched with internal resistance of the battery, because if the battery is full and these resistances are matched, maximum power will be transferred to the motor to turn on the engine. So that's all for today's lecture. So to make this video, I take help from the link which is given here, and I also take some different books as a reference, like the book of Abhijit Chakraborty, Circuit Theory and Synthesis. So that is a very good book. I always prefer to read the books, and I suggest guide my students, please read the book, solve the related problem from the books. There are so many exercise examples in different books, so please solve it repeatedly. Then only the concept will grow and you will be able to solve the difficult problem. You will be successful in your life. So that's all for today. Thank you, everyone. Thank you.